Okay, let's look at this propagation of uncertainties issue a little more in detail, a little more carefully. From the exam review, we had this question, and we talked about already how the time constant for this configuration would look like R over 2 times the product of these capacitors over their sum, and we wanted to work through basically the propagation of uncertainty piece is we want to understand delta tau, the uncertainty over tau. And so let's just walk through that example. So think of this as our function, tau as a function of r, c1, c2 equals that thing. And so the first thing that we want to do is take partial derivatives of that with respect to each of the constituents. So tau dr, we would just pick up a factor. R would go away. D tau d c1. So in this case, now we have a quotient. So we'd have our R2 times low d high minus high d low all over the square of the denominator. The partial with respect to C2 would look pretty similar to this. Now we'd have low d high minus high d low all over that square of that denominator. Square here. Okay. So now that we have the partials, the next thing that we want to do is, oh, and I should say where we're headed with this is we're going to assume basically 10% component values, i.e. we're going to assume that our uncertainty, delta R, delta C, etc., is 10%. Okay, so the next step in the procedure, if we have the partials, we can find delta tau by adding the partials times a step in that direction. And you can think of this as, these partial derivatives tell you the slope along these different dimensions in this three-dimensional space. And so if you want to find out how the whole function changes as you change C and R1 and C2, what you do is you multiply a little step, these delta R's and delta C's, times the slope along each of those dimensions. So the slope are the partial derivatives. And then you add them up, and that tells you how the whole thing is going to change. In other words, it tells you the delta tau. So let's put these ingredients together. So we'd have C1, C2 over that plus. Notice, actually, we can simplify this a little bit. We have C1. Let me put this in a different color here. We have a factor of C1, C2 minus C1, C2. So this and this would go away. And this would be actually R C2 squared over C1 plus C2 squared. And this would be similar. This C1, C2 piece would go away, be canceled by that one. So we would have R over 2 C1 squared over that. So let's put those ingredients together. See, once you kind of get in the swing of this, it's not so bad. Just practicing some of your calc skills. And then generally what we do is this is telling you, the uncertainty in tau. It's convenient to express this as a relative uncertainty. So in other words, if we divide by tau, so what we would need to do is divide our function by, our terms by the original function. And so recall the original function was r over 2, the product over the sum. So if we divide everything by that, so divided by plus, we'll just take a second here and be really explicit and write it out. And you will see that this will really collapse down a lot, simplify a fair amount. So what all is going to happen? This stuff would go, this would cancel. This factor of 2 would cancel. So this would become just delta r over r, and we've seen that sort of expression a lot in uncertainty analyses that we've done so far. Here we would have, a bunch of stuff would cancel. This would cancel. We would lose that factor. We would lose one of those. And so this looks like we would have C2 over C1 times delta C1 all over C1 plus C2. And plus, see, this would go away, lose one of these. You can see they're kind of going to be symmetrical here, look very similar. So that would be our delta tau over tau expression after we simplify things. And notice this is a little more complicated than the ones that we had done before, but that's because this function had, a quotient in it. And we can evaluate this numerically. So let's evaluate this numerically. Basically, we're going to assume that everything is good to 10%. So what that would mean in terms of component values is that delta r would be 10% of r. Delta C1 would be, 10% of C1. Delta C2 would be 10% of C2. And actually, we're going to make an additional observation here that will simplify things. If we look back in the original problem, this capacitance 2 was 2 times capacitance 1. So in other words, C2 was 2 C1. So we can put that piece of information as well. So that means that, delta C2 would equal 0.2 C1. So in other words, I can just put C2 in terms of C1, and that will allow us to cancel the actual values without having to put them in. So let's do that and just see what this spits out. So delta r over r would be 0.1 r over r plus 2c1. I'll just put these in parentheses to kind of emphasize that I'm substituting them in. 2c1 over c1 times 0.1 c1 divided by c1 plus 2c1. And here we would have c1 divided by 2c1 times 0.2 c1 by c1 plus 2c1. And so you can see some of this then would cancel. You can cancel these factors. You can see this is actually 0.1 plus 2 times 0.1 c1 over 3 c1. You could cancel those as well. And then this would be 1/2 times 0.2 c1 over 3 c1. Cancel those as well. Long story short, we boil this down. We would have 0.1 plus 2/3 times 0.1 plus 0.2 times 1/6. And so this is actually the same thing as 0.1 over 3. So in other words, we have 0.1 plus 2/3 0.1 plus 1/3 0.1 equals 0.2. So long story short, for this sort of just numerical example, delta tau over tau is going to equal 0.2, and this was for, delta R, delta C's that were 10%. And this is kind of neat, I think, in that it shows you that how the uncertainty in R and C that are that are necessary to determine tau, how those uncertainties impact the uncertainty in tau itself. So if you were building a circuit or something, an oscillator, and you wanted the time constant to be a certain, to have a certain uncertainty associated with it, this would tell you how good you would have to do with your values for R and C, and it maybe gives you a little bit different context for talking about propagation of uncertainties and how this is, this would be useful to useful and relevant to engineering situations. So hopefully that helps. The question that you'll see on the exam is not going to be quite so complicated in terms of these quotient rules and stuff. So as long as you can do this kind of procedure, you should be pretty good.